Manipulating deformable objects, especially elastic bands, presents significant challenges for several reasons. First, elastic bands have near-infinite degrees of freedom and complex dynamics, which require the agent to explore extensively, leading to high sample inefficiency. Second, the task becomes even more difficult due to partial observability. Effective manipulation of deformable objects requires an accurate, occlusion-robust, and consistent representation, which is hard to achieve from partial observations. To solve this problem, we set our problem to learning compact deformable object representation from visual sensory observation. We propose a novel implicit neural representation learning model for elastic deformable object manipulation, which we term Inr-Dom. Inr-Dom is a dual-stage implicit neural representation learning approach designed for elastic object manipulation. In the pre-training stage, Inr-Dom learns geometric features to ensure consistent and occlusion-robust representations. In the fine-tuning stage, Inr-Dom refines the latent representation and learns task-relevant features to facilitate reinforcement learning. This section provides an overview of the Inr-Dom. The Inr-Dom performs shape reconstruction in the pre-training stage using an implicit signed distance function network. First, the encoder phi maps the partial point cloud to a latent representation, which is then used by the HyperNet decoder to predict the signed distance function network weights. We compute 5 loss terms with 3 key losses. Skeleton loss ensures alignment of the reconstructed mesh's medial axis with the ground truth. SDF loss enforces correct values of the signed distance function and gradient directions for on and off-surface points. Consistency loss ensures the latent representation of the partial point cloud is close to that of the complete point cloud. This is a demo of mesh reconstruction using the pre-trained encoder in a simulation environment. In the fine-tuning stage, we learn task-relevant features and policies through reinforcement learning. The agent stores transitions in a replay buffer and updates the pre-trained encoder, critic network, and actor network. Additionally, we generate queries and keys for contrastive learning from the buffer and refine the encoder's latent representation using a temporal contrastive loss. This is a visualization of the latent space. In A, the trajectories begin from either the top left or bottom right regions, depending on the randomly selected twist direction for the rubber band's initial state, and converge to the same latent representation at the end. In B, the top left and bottom right meshes show that the fine-tuned encoder clusters rubber bands twisted in the same direction closely, while mapping those twisted in opposite directions farther apart. This structured latent distribution enhances policy learning by providing a coherent and discriminative state representation. We tested our method in sealing, installation, and disentanglement tasks in simulation. This figure shows our environments in simulation. In 3 simulation tasks, Inr-Dom outperform all other methods, achieving the highest task success rates, an average rate 37.7% higher than ACID, the next best DOM method.